All right, so here we are. Last video for Unit 4 of linear momentum. Okay, so we're now going to talk about collisions officially. In the last video, we did two problems. One was a collision, but the other was an explosion. So let's talk about collisions specifically. So a big application, or the application of a conservation of momentum, will take the form of collision, right? So you can have billiard balls colliding. In fact, that's snooker, which is an English version of billiards. And then you have, football. It could be talking about that. This is an Army-Navy game. I think, unfortunately, in that game, Army lost. They lost like 11 straight to Navy until recently. Okay. Now, when we analyze these collisions, we're going to focus on two of those conserved quantities that we've spoken about. Right? We're going to focus on conservation of energy, which is Unit 3. And we're going to look at the stuff here from Unit 4, which is linear momentum. Okay. And then you have the fourth quantity, or the third quantity, which we'll talk about when we do rotation, which is angular momentum. So there are two types of collisions. There's elastic and inelastic. And really, the analysis piece is how we determine which collision it is. So as you can see, for elastic collisions, momentum and total kinetic energy is conserved, right? For inelastic collisions, momentum is conserved, so momentum is always conserved, but total kinetic energy is not conserved. So what they like to do with the elastic collisions, they may talk about like what percentage of the kinetic energy is lost, or what's the difference in kinetic energy. That right there will tell you that is an inelastic collision. Now, elastic collisions, that's kind of like our ideal physics world. Right? Okay. But most collisions in the real world, regardless, right, is that they're inelastic. And then you may hear the term perfectly inelastic. Right? Perfectly inelastic collision means that the objects will stick together in the end. So our scenario with the railroad cars in the previous video, that was an inelastic collision. Okay, they hit, they coupled together, and they went off as one giant mass after the collision. For elastic collisions, I'm going to change the color because this is going to be very important. So for elastic collisions, you can go and do the algebra, but you're going to find that the initial velocity plus the final velocity, right, and VA prime or VAF, VAI, right, they're going to the sum of the two velocities of the objects are going to equal each other. Okay, that's just there's a lot of algebra involved in that, but that's going to help you, especially if you have to find the velocity after, both velocities after with elastic collisions. Okay, so the example problem that I chose for this video is a special case. This is what we call a ballistic pendulum. Okay. It is an inelastic collision. The way to think about ballistic pendulums is that there's three parts. There is a launch part, which if it's coming from like a spring-loaded, device, that's going to be conservation of energy. If there is a, then you're going to have the collision of the projectile into the device. So if I'm looking at this particular picture, right, this is going to be conservation of energy. Then it's going to go into this block, which would be your conservation of momentum. And then it's going to swing back and up to a height. So that's the third part, and that's our swing. And that's going to be conservation of energy. Now, because this is a pendulum, right, they can give you either the angle, they can give you the height. So there's going to be like different things that you would have to apply here. Okay. So here's the question we have. We got a ballistic pendulum. The projectile has a mass of m fired into a large block of mass m, capital M, which is suspended like a pendulum. As a result of the collision, the pendulum and the projectile together swing up to a maximum height. Determine a relationship between the initial horizontal speed of the projectile and the maximum velocity. Okay, so we're not worried about the launch. So in this problem, I don't have to do that part. So I'm looking at the collision and the swing. Okay, so the collision, right, is conservation of momentum. So I have P before equals P after. Okay, and so what happens is my initial velocity will be the velocity coming out of the barrel will be my velocity, my initial velocity. And so I would have MVO. And now this is an inelastic collision because they hit and stick together. That's going to be M plus lowercase m times V. But something to note is that this V, the final velocity in my collision, becomes my initial velocity of my swing, right? And so that's what I'm going to solve for here. Say MVO over big M plus M, okay? So that's, my final velocity of my collision, which becomes my initial velocity of my swing. And now I go to energy, right? So E before equals E after. Okay, so in a swing, right, this is the height, this is what I'm looking for, or this is the kind of relationship I'm looking for with my velocity. Okay, so before it, before it moves, it only has, the only velocity is the bullet, right, or the bullet block system. And then at its maximum height, my velocity is 0. Okay, so before I only have 1/2 mv squared. Now let me do it this way. That m is 1/2 of m, capital M plus lowercase m, v squared. And that's going to equal, did it again, that's going to equal my total mass, m plus m gh, right? Because I only have, it stops, I only have potential energy at the top. So something you'd see here, this cancels that. And so if I'm solving this in terms of, if I'm solving for v or h, right, I end up with the square root of 2gh. But that doesn't relate my initial velocity. But this and this are equal. So I'm going to say little m over VO, or little m times VO equal, divided by m plus big M, or big M plus small m, right? Square root of 2gh. And I'm just going to do a little bit of manipulation of my equation there. And I'm going to get my initial velocity is equal to my total mass over the mass of the projectile times the square root of 2gh. So there's relating my initial velocity and my height. Now, you could solve this for height as well, and it ends up looking like mvo squared over 2g times m plus m, like big M plus little m squared. So these would be two acceptable answers. One solve for height, the other solve for initial velocity. It's just, I mean, you could do whichever one you want, but you got to get to this point right here, because if you don't get to that point, you're not going to be able to solve for the rest of it. Okay? So again, that's a special case. It's an inelastic collision centered around ballistic pendulums. The AP test does like to use ballistic pendulums. Okay, that's why we're going to make it a point to look at this particular question. And this could be an AP question because notice that my equation, it's a derive an expression type question. So that concludes Unit 4, Systems of Particles.